Welcome to qnawire.
Our question says that a 2,140 kilogram railroad flat car, which I write as M sub C here, can move with negligible friction, and it's motionless next to a 242 kilogram sumo wrestler, which I label as M sub S. And this sumo wrestler runs at 5.3 meters per second along the platform parallel to the truck, and then it jumps onto the flat car. What is the speed of the flat car if he then does A, just stands on it, B, runs at 5.3 meters per second relative to it in his original direction, or C, turns around and runs 5.3 meters per second relative to the flat car's opposite to his original direction? Okay, so since he kind of becomes part of the flat car, we're going to assume we can use conservation of momentum here. Also, we're going to call the initial direction that the sumo wrestler is running the positive direction. So I write Vs of 0, the initial velocity of the sumo wrestler is 5.3 meters per second. So for part A, where he just jumps onto the flat car, we have the initial momentum, which is just the mass of the sumo wrestler times the initial velocity of the sumo wrestler, is equal to the mass of the sumo wrestler plus the mass of the railroad car. And since they're together, they're going to both be multiplied by the velocity of the railroad car. That's the final velocity, so we'll write it as Vc sub f. Okay, so now we can solve for the final velocity of the railroad car. This equals mass of the sumo wrestler times his initial velocity divided by the combined mass of the sumo wrestler and the car. Okay, and you plug in those values into this relationship, and this comes out to be 0.54. Make that a little neater. And the units here are meters per second. We can box that in our solution to part A. Okay, we'll open up a new page here. Now for part B, it says that it wants us to consider a scenario that after the sumo wrestler jumps on the railroad car, he continues to run in the original direction at 5.3 meters per second. So his new velocity, we'll call this the Vs prime, the sumo wrestler velocity here, is equal to the initial velocity of the sumo wrestler. Okay, so we can rewrite our conservation of momentum, same initial momentum as we had previously in part A, but this time we have the mass of the car times the final velocity of the car plus mass of the sumo wrestler, and it's the final velocity of the car, plus the final velocity of the sumo wrestler, which we said was V of S prime, right? Okay, well, we can simplify this since so we have V sub S times, if you apply it by this, since we said that is equal to the initial velocity of the sumo wrestler, this is V sub S 0 plus M sub C plus M sub S, and both of those are multiplied by the final velocity of the railroad car, which is what we're trying to calculate. But you can see that the mass of the sumo wrestler times the initial velocity of the sumo wrestler on both sides of the equation canceled out, so that's equal to 0. Therefore, the final velocity of the car also has to equal 0. All right, and lastly, for part C, we have the final velocity of the sumo wrestler is equal to, now he's running in the opposite direction, minus V of S 0. Okay, so you can write this as V of S times V of S 0 is equal to mass of the car times the final velocity of the car plus mass of the sumo wrestler times final velocity of the car minus v of s, 0. Okay? So this time we can rearrange this to solve for the final velocity of the car, which is equal to the mass of the sumo wrestler multiplied by final velocity of the sumo, or the initial velocity of the sumo wrestler, excuse me, plus the relative velocity of the sumo wrestler, which we determined to be S0, divided by mass of the sumo wrestler plus mass of the car. So you plug these values into the equation, and this comes out to be 1.1 meters per second. And box that into our solution to part C.